Nuclear power production in India. Before going into this, I'd like to say that nuclear power production is one of the most efficient means of power generation that human beings have discovered till date, because it's thousands of times more efficient than the same amount of coal or crude, and it has a whole lot of recycling possibilities. It is clean in the sense it does not emit those polluting gases, and with the advancement of technology we can expect better things, but safety is a important caution that we have to exercise. So how is nuclear power generated? In a sense, you have heavy metals which have heavy nuclei, and they spontaneously and naturally decay into lighter metals and generate heat. It is this heat which we use for energy. The most common heavy metal which is found in nature is uranium, and although most of its isotopes are having small half-lives, which is why they are not found naturally, uranium 238, 235 and 233 have pretty large half-lives. 238 has a half-life of billions of years, 235 millions of years, 233 hundreds of thousands of years. So this one doesn't seem to be too much, which is why this is not found in nature. And if you take any natural sample of uranium, about 99.3% of it would be uranium 238. 0.7% of it would be the 235 isotope. But unfortunately, the 238 isotope is not fissile. It is fertile. 235 isotope is fissile. What do I mean by this? The 235 isotope can directly participate in a spontaneous chain nuclear reaction, and uranium 238 can be converted into a fissile material. That's why it's called fertile. So our effort is to increase the percentage of the 235 isotope in a process called enrichment. If you enrich it to 1%, it's called slightly enriched uranium, 3 to 5% is low enriched uranium, and more than 20% is weapons grade highly enriched uranium. So for that, a centrifuge is used. Okay, so how is energy actually generated? Natural uranium will consist of uranium 235 and uranium 238. So when you bombard it with neutron, the uranium 235 will break into lighter metals like barium, krypton, and it will release other neutrons. It is these neutrons which will further bombard other uranium 235 nuclei, and that will release further neutrons, and therefore you'll have a chain reaction. It has to be controlled, so we must have a moderator to absorb the excess neutrons, and at every stage heat is produced. So heat is produced in this stage, then heat is produced here, heat is produced here. Every time a neutron bombards it, heat is produced. It is this heat which has to be captured with the help of a coolant, and water is to be converted to steam, which can run turbines to generate electricity. Fair enough. Otherwise, if it's uncontrolled, it becomes an atom bomb kind of thing. If this neutron hits the 238 isotope, it transmutes, it absorbs that neutron, and this is fissile, so it directly undergoes fission. This is fertile, so it absorbs that neutron and becomes a fissile material called plutonium 239, which when bombarded with a neutron will undergo a similar process as this. Once this is clear, it is understandable that anyone would want to use a slightly enriched or low enriched uranium rather than natural uranium, because that would ensure greater fission. India presently uses natural uranium mostly, but if enriched uranium is used of 1%, 2%, then definitely the efficiency of power production can increase. That is one aspect. Another aspect is that India has low reserves of uranium. about 1% of the global reserves. 33% are there in Kazakhstan, and there is in Canada, but India doesn't have much uranium reserves. India has about a quarter of thorium reserves of the world, mostly in the monazite sands of Kerala. So what Homi Bhabha came forward with was a 3-stage nuclear program for India, which I shall discuss right now. In the first stage, he envisioned a pressurized heavy water reactor, something which is widely used up until now. This is the first stage. The first stage. So uranium 238 plus 235, that is a natural uranium, would be input. The 238 would turn into plutonium 239, and the 235 would turn into heat. This is the first stage. In the second stage, it is this plutonium 239 which will be input into the second stage, which is known as a breeder reactor. Breeder reactor. Apart from plutonium 239, we will also add natural uranium, that is uranium 235 and uranium 238 combination. Now these two would generate heat, whereas this would transmute to further plutonium 239. And the main idea of this breeder reactor is that it would breed more plutonium 239 in its output than it takes in the input. So there will be a huge lot of plutonium 239 which is fissile, and therefore it can be reused in this nuclear reactor, or it can be used in other breeder reactors, can be used in various other breeder reactors, and whatever remains can be used to fill a reservoir. If I consider this as a reservoir, over a certain period of time, plutonium 239 would build up. When there is sufficient plutonium 239 which has built up in this reservoir, it is at this point that I would add uranium it is at this point that I would add thorium, which is 92 and 232, and this would cause the transmutation of thorium into uranium. Thorium is 90, uranium 92 233, and just like uranium 238 was fertile and it gave this fissile plutonium, similarly thorium is fertile and it gives this fissile U-233, which is the end product of the second stage. So this entire thing is the second stage. Now I come into this third stage with uranium 233 in my hand. I add this uranium 233, little amount of uranium 233, and a good deal of thorium which is readily found in India, and I add this in a breeder reactor, which is a thorium based breeder reactor, because the main hero in this entire reaction is thorium. So this is a breeder reactor once again, but thorium based breeder reactor, and what it produces is further uranium 233, which can be reused in this reactor, and it can be sent to other reactors as well, other third stage reactors. So that India has a lot of thorium reserves, and what India has 1% of the global uranium reserves, not too much, but still enough to continue this first stage and this second stage uranium supplies, and that would give uranium 233 for the third stage. So once India enters the third stage, it will become self-sufficient with whatever little uranium reserves it has and the large thorium reserves that it has. But to run, and this is chronological, so India hasn't even entered the second stage as of now. The first nuclear breeder reactor would be the one in Kalpakkam called the prototype fast breeder reactor, and if it happens in 2022, it will be really good because it is long due. So once that happens, the second stage will be entered. Then after a few decades we can enter the third stage. But if we use more uranium, it will be quicker for India to enter the third stage. So for running this first and second stage, India requires a large amount of uranium. So we need to import uranium, at least for the first and second stage. And these first, second, third stages are chronological stages. So we need to import uranium. Now India does not have much uranium. And in 1968, there was a non-proliferation treaty in which there were 5 countries. United States, France, UK, Russia, and China. They had developed nuclear weapons, and in order to prevent any further development of nuclear weapons by the rest of the countries, a disarmament treaty called NPT, Non-Proliferation Treaty, was signed. And as soon as India tested its nuclear test in Pokhran in 1974, in order to put sanctions and in order to control the export-import market of uranium internationally, a nuclear suppliers group was formed in 1974. And as per the rules of this group, India could not import uranium from the other countries, which became a barrier for India's development. And therefore, in the period of 2005 to 2008, a civil nuclear deal, that is not for military purposes but for civil purposes, India requires uranium, so please allow India to import uranium from the countries which have uranium, that is members of the NSG. So this was a civil nuclear deal between US and India. So what really happened in this deal? First of all, an NSG waiver was given. That is, even without being a member of the NSG, even without signing the NPT, India can still import uranium based on certain conditions. That there would be IAEA inspections, also known as safeguards, on the civil nuclear sites of India, and that India would separate its civil and military nuclear facilities. So the 1% uranium reserve that India has must be sufficient for the military purpose because it does not require much uranium. For civil purpose, India needs to import uranium, and to check whether this imported uranium is not misused for enrichment unnecessarily and creation of nuclear weapons. To prevent any proliferation, the IAEA would do its inspection of these civil nuclear facilities. And India voluntarily came forward with a no first use policy as well. So after this, India could import uranium, and this thing is happening, but it is expected that once India enters the third stage using the thorium reserves of India, it will be good. And further, the United States, many experts in the United States had said at that point of time that this civil nuclear deal, which was passed using a Hyde Act or 123 agreement in the United States, is actually beneficial because even the US and the other countries of the world would be able to learn from the indigenous technology of India, of the breeder reactors of the 3-stage program which the legendary Homi Jahangir Bhabha has envisioned for India. So the world has a lot to learn from India insofar as this nuclear technology is concerned. And there is a lot of debate about reprocessing the spent fuel. Here I had said that this plutonium 239 is produced, but in general from this pressurized heavy water reactor, some countries have boiling water reactors or pressurized water reactors, whatever name you call, it produces this spent fuel, spent nuclear fuel, which contains mostly the uranium oxide and other radioactive isotopes, and it also contains plutonium 239. So in order to use this plutonium 239 in the second stage, you have to take this spent fuel and you have to reprocess it, reprocess this thing in order to extract this plutonium and reject the rest. Now this is an expensive process first of all, and what do you do after you've extracted plutonium? You throw it away into the seawater. This is not environmentally friendly. Furthermore, when you are reprocessing it, you also classify the nuclear waste into 3 categories, or you segregate the nuclear waste into 3 categories: low radioactive, medium radioactive, high radioactive. And the low radioactive is often disposed into seawater, which is definitely not eco-friendly, and ultimately humans will consume the fishes and the water. So radioactivity has to be prevented. So there is a lot of criticism as to whether the spent fuel needs to be reprocessed at all. They say that just dispose it off safely. But if safe reprocessing of this fuel can be ensured using some good technology, then it will be good, because you'll be able to extract the plutonium 239, without which how will you run the second stage of this 3-stage nuclear program? So a balanced technological approach needs to be thought about. That is it for now. Stay tuned. Do subscribe, share and like. Thank you.